Well, good evening, everyone. I'm very pleased to welcome you to this evening's AIAA Los Angeles section event. I'm Jeff Puchel. I work for Northrop Grumman over in Redondo Beach, the Space Park campus. I've been very active in the Institute over the years, including being someone involved in these events. The speaker tonight is my distinguished colleague, John Ehrenberg. John is a fellow at Northrop Grumman. He's been involved, I think, in every major great observatory, certainly the ones at TRW and Northrop Grumman for the past 20 years or so. John has his degrees from UCLA. He's a proud Bruin. We were talking about that just before starting this event. And he's intimately involved in the future as well. And that's what we're going to hear about tonight. John is going to talk about future architectures for great observatories. So please join me in welcoming John Ehrenberg.
Thank you, Jeff. For those online, if you have audio or visual issues, hit the chat. Jeff will be watching on the tablet. So if I need to speak up or move or be a little louder, I will do that. So I like to start with this particular image. One of the reasons is it sends a message to me of one of optimism. So this may not be well known to everybody, but this was actually the first released image from James Webb. This was unplanned, but the results of initial alignment were so promising that the program decided to share this with the world. So at this point, the alignment of the telescope had only been completed on axis. It still had to be done over the full field and for all the instruments. But the star that you see here was chosen very carefully to be all by itself. And of course, what you see is it's photobombed by roughly 200 galaxies that heretofore had not been known to science. So even though there was some risk in releasing this and not completing the alignment, the project went ahead with it anyway, and it has always expressed to me the optimism that goes along with these programs. And at this point, what was called JWST had probably been about 38 years in the making. So that optimism was hard earned, but watch for that again. So I'm going to talk to you. Basically, I'm taking a problem off of my desk. So as Jeff indicated, I've been involved with the large NASA observatories. My actual full-time day job is observatories at all scales for all 4 science disciplines, but I can't tell you every problem I'm working on. So I'm going to pick the one that deals with the Habitable Worlds Observatory, and I'm going to put it in terms of my job essentially as an engineer. So small overview of the job. We're going to go through a brief preamble. I know that there are some students online, or at least I hope the ones that I invited made it, because part of the way I've constructed this talk is to not only communicate to the professionals and the others in this room and online what's going on with this particular mission, but this is also essentially a methodological discussion of how engineers go about making hard decisions. And we'll talk about why some of these are so hard to do. So I also want to talk about why are we considering tomorrow. Briefly talk about the design process. I will introduce some of the challenges in imaging an extrasolar planet, specifically what we call an exo-Earth. It's an Earth analog. You'll find out it's a fantastically difficult problem. We're going to talk about something that I've coined the 3 space ages. This is essentially a historical view of the development of our field, broken into eras that are clear and distinct and have a different design paradigm and ethos. And since we're on the cusp of a revolution with a whole bunch of stuff about to happen, Do we really want to design our next great observatory like it's 1985? The answer to that is, of course, no. And then here's part of the hard part, is we are standing on the edge of this potential revolution in what we do, except none of it's happened yet. Some of it, yeah, a little bit, but it's not 2045 yet. It's not even 2035. So what is the world going to look like when we get to the design freeze point, and have we put in the right architectural hooks to make the best deal for habitable worlds? So habitable worlds, like every other mission, is going to have a certain amount of money and a certain amount of time and a really, really, really hard problem. If you don't want to spend money on stuff that doesn't work the problem, and we want to get the best deal for the customer. And how we do that is changing radically, as literally almost as we speak. So we'll talk about two cases and how we start from essentially a series of cartoons and work towards, hopefully, a very quantified, rational design process, so that when it comes proposal time, we can write a successful proposal. Okay, so remind everybody that I'm an engineer. I make products for customers. For a profit-making company. We hope to be successful and sell more of them. Two of the products I've worked on are right here, the Chandra X-ray Observatory and the James Webb Space Telescope. Basically, I've always told students, told myself, anybody that will listen, I'm an engineer. My job is to invent tomorrow, the products of tomorrow that my customer wants to buy. It's that simple. My customers just happen to be scientists. If we're selling toasters, I would say the same thing. I'm not. I'm selling space telescopes. Okay? But before I can invent tomorrow, I have to imagine. Right? So imagination comes first, not only in the dictionary, but in the design process. So again, this is part of the methodological part. We want to understand how to start imagining this engineering environment of the future. We're going to do that with a little bit of creativity. We're going to throw a wide net, collect a lot of ideas, some of which will pay off, some of which won't. It's just the way the cookie crumbles, as my late father would say. Broad span of ideas means we don't leave something off the table that could potentially pay off large. Quantification. What separates professional engineers out from others. As Lord Rayleigh says, if you can't quantify it, you do not understand it. So, the other favorite quote is all models are wrong, some are useful. Okay, so in this case, I'm not worried about getting the analysis and the little models that I'm going to show you wrong. I know they're wrong, but they're infinitely better than nothing. And then there'll be another generation, and eventually we'll sneak up and surround the truth. But in the meantime, we're going to learn a lot about the playing field and what pays off, and where does the money go, and where should we be spending our time. And again, this quantification goes to the assessment of cost and risks and benefit to the program. And when we're successful, habitable worlds will be on a postage stamp, should such a thing still exist in the 2040s. Okay, this is also for the students. This is a bit of a criteria of what makes a good systems engineer. This comes straight out of the class that I used to teach, what makes a good systems engineer. So hopefully I embody most of these properties. I really want to pull your eyes to multidisciplinary, multidisciplinary, big picture view, understands this is code for interactions amongst different parts of the design and the relationship between design parameters and performance. That's what I mean by these partial derivatives. Really comfortable with change and uncertainty. I think anybody living today knows that we all have to. Basically likes people, because there's going to be a lot of people involved in this. Went to the Habitable Worlds 25 conference there were 1,000 people signed up to help develop this mission. So there's a lot of people to talk to, a lot of people to convince. This is much social engineering and communications as it is an engineering job. Okay, so why do we consider tomorrow? That is, why do we consider what's going to happen? What could we need tomorrow for these kinds of customers? So we're going to ask the question, why imagine tomorrow's space observatories? And I'm going to remind everybody that astronomy, astrophysics is an observational science. All of the discoveries, certainly since 1609, have been made with the aid of a telescope, and one could argue even before that, Tycho's measurements were the result of superior instrumentation and technology, even going back to the Nilometer and other things in ancient times. So observation trumps physics. Theory catches up with observation. Basically, observation takes hardware. When we make these great leaps, we have changes in imagery. This is the same supernova remnant, Cassiopeia A, as imaged with the Einstein Observatory that was built at Space Park in the 70s. And this is the same image built with Chandra, built in the same place 2 decades later. The colors indicate elements. You can see the neutron star. This was essentially Chandra's first light image. It's also interesting to note that everything necessary to make DNA has been directly detected in the supernova. So as we're going to talk about the search for life, that's step one. Can't have life without the requisite atoms. Okay. This has been going on for a long time. In case you don't recognize this handsome fellow, that's Hans Lippershey, generally credited with the invention of the telescope. Here's his patent application. Like a lot of the ones written in English, it's impenetrable even to the inventors. But you probably recognize this guy even more. Galileo, he didn't invent the telescope, he improved the technology. And then he used the technology to make observations, and then even more critically, he wrote about it in perhaps one of the most important books in Western science, The Starry Messenger. So this technological progress has been going on for over 400 years. This is a plot of the largest telescopes that humanity has built. You can notice a significant slope change here with the invention of the multiple mirror segmented telescope. If we zoom in, this is the largest ground-based observatories, and I've added space. And if you creatively lay a line over it, this is not a rigorous fit, literally took a ruler and laid it across. You can see that everything's progressing at roughly the same pace, which means no matter what the science is, tomorrow's demand from science will be for a larger, more sensitive instrument. This is why we want to consider tomorrow, again, I'm an engineer. I work for folks that want me to sell hardware and make a profit. I have to be ready with what the market is going to want when it comes time to sell. This is one of the fundamental reasons to consider tomorrow. If you want to call it market research, that's certainly true. For those of us in the science business talking to scientists, we don't call it that. We tell them we're doing this to advance science and the field. The design process has about 8 steps. We're going to concentrate on the front ones because what we're designing is the concept of the implementation of some new technologies that we're going to be talking about. So it's critical to understand what the customer wants, ask the design problem to address their question in a way that can be addressed and answered. Again, here comes creativity. All the possible options, all the ways I can solve the customer's problems. Selecting the best option after we know what he wants or she wants. and then ultimately understanding how the design or concept works. And as I'll explain, so we know how it fails, so we can rectify those failures. Okay, so again, we want to concentrate on the what, not the how. Who are the various customers? How might they be satisfied? So again, we're talking about how to include and define the architecture for as yet defined telescope. So basically everybody I talk to is a customer. NASA folks, users, my colleagues in industry, my managers, my colleagues here. So basically it's everybody. So it's a little unspecific. Remember I told you up front, system engineers got to be used to a little chaos. This is part of the chaotic time in the development of the program. We want to, ask the correct question to get to the right answer. So the way I remember this is a little example I made. Let's make some chips. Okay, there's a fundamental question about, are we making potato chips, chocolate chips, or microchips? All of which are very different. Okay, so really what we need to know is we need to know the difference, and we need to be able to appreciate the subtleties of what we're being asked to build. So being asked to build an observatory to collect X-rays is similar to, but not the same, as one to detect an exo-Earth or the beginning of time, which is James Webb. We want to think through all the problems, come up with as many ways to determine the solution as possible. We don't want to leave something on the table that later a competitor or somebody else pops up and says, oh, look, if you just use the orange crayon, it works. You don't want to be in that situation. So you basically want to avoid a failure of imagination. For those of us of a certain age, that has a very direct meaning. That's a phrase used by Frank Borman to describe the situation that led to the Apollo 1 fire. Nobody could imagine putting 3 people inside a capsule full of stuff that would burn in high pressure pure oxygen with a door that opened in could be dangerous. 3 people paid a heavy price for that mistake. We're going to come back to that specific event in a little bit. We want to select the best option. We want to have a rational process for evaluation. One of the things that I'm going to talk about later is how to set up a rational process to sort through all the technological choices. We want to understand how the design works, or in this case, how the concept works. So essentially, we understand how it doesn't work. Okay? So by understanding how it fails, it tells us how the design needs to be changed and upgraded so it doesn't have that failure mechanism. This is what we spent years and years on James Webb doing. Repeated cycles of testing and analysis showed us increasingly subtle modes of failure until we got enough of them out that everybody was comfortable with launching. So the Habitable Worlds Observatory is designed to detect an extrasolar planet around the sun. Typically, the typical problem is detecting Earth around a sun-like star fairly deep into the galaxy, about 30 light years, 10 parsecs. And when you do that, the exo-Earth is, first of all, 10 to the minus 10 fainter than the host star. That's 10 billion. And because it's located 1 astronomical unit away and you're 10 parsecs away, it's 1/10 of an arc second. Those of you that don't speak that or don't speak milli arc seconds, it's a 36,000th of a degree. Okay, so you got something really, really bright next to something that's really, really dim. This is occasionally described as trying to find, standing a nautical mile away from a lighthouse and trying to see a firefly an inch away from the lighthouse. Turns out if you go to the library, that's 100 times easier than this. I looked up the luminosity. The ratio is 100. It's only 10 to the 8. That's still not very easy. Okay? Achieving this contrast, that should be an exponent, requires ultra stability, that is the wavefront. The errors in the path length across all of the paths where light gets collected has to be stable to roughly 3 orders of magnitude better than Webb. Webb is stable to tens of nanometers. This system needs to be stable to tens of picometers. It's really not a unit that most polite engineers use. It's a millionth of a micron. Tiny. And the planets are really dim. Just by themselves, even if the star wasn't there, right? Because most of these target stars, if you're an observational astronomer, are 5th to 7th magnitude. 10 to the 10th is another 25 magnitudes. 30-ish, 30 plus or minus a few magnitudes is comparable to the dimmest, most distant star ever detected. So we need a large, stable telescope. Big, stable telescope, well beyond the state of the art. So you should be thinking this is not only challenging, this is going to be an expensive proposition, which it will be. The idea is, how do we use the tools that are coming to best effect so that we can spend the money on the part that returns to science. Okay, and here's a pictorial representation of how far we can reach into the galaxy with different sizes of telescopes. Not unexpected, the bigger the telescope, the further you can see in. And at a given density, the deeper the volume, the more stars you can see. So we need a big telescope to not only have lots of targets, but to collect the light from those targets and then ultimately take a spectrum, which could take up to days, weeks, or months, depending on how bright that target is. An incredibly challenging problem. Okay, so scientifically, and you should be seeing a slow-moving movie here, that is simulation of an extrasolar system as observed. The Earth's system observed 3 light years away. Habitable Worlds Observatory is designed or aims to identify and collect spectra from 25 Earth-like planets. That's somewhat in flux, what that exactly means, how big the telescope has to be, how far to go, because again, like Webb's first light targets, we don't know where they are. Right? There's a number of stars that we can count up the 500 closest stars, but which ones have Earth-like planets, that's yet to be determined. This is going to require at least a 6-meter mirror, so it's at least as big as James Webb. The desire is to enter the formal development by 2030 and launch it in the mid-40s. It's been deemed to be serviceable, with that left very unspecific, and that's one of the things that we're going to address. And it also is the intention to be very long-lived. Keep in mind that most of the big spacecraft, the 2 observatories I worked on, had a requirement for a 5-year lifetime. Guaranteeing that it was going to work under every bad thing that could happen was a challenge, and drove costs, and drove schedule. If someone were to scratch out the 5 and say 50, the price of that spacecraft is going to go through the roof. We don't want to do that. What we want to do, I don't know, and that's what the rest of the talk is devoted to. Okay, so one more thing. I want to talk about the space ages, and the reason is because designs are representative of the era in which they are developed. If you take a look at a 1960s spacecraft, it's designed around the technology of the time. There's limited use of computers, no glass cockpit. It looks like a B-17 with a rocket on the bottom of it, right? With the exception of maybe no cable controls, right? As we moved into later eras, there's more computers, more solid-state electronics, etc. So this is very much the same were these large observatories that are representative of their development era. Okay? So these things take a long time to develop. The first meetings for James Webb were in the mid-'80s, even before I was hired by TRW to work on the contract that we just won for what was called AXAP. If you're interested, since this is going to be recorded, this is a particularly good paper that just came out that talks about the genesis of the idea and all the puts and takes, essentially this talk, but for James Webb. We're going to define the revolution that we're on the cusp of. Lots of things, if you're in this business or even a fan, you will hear, you can't get away, you can't look at your phone without some news blurb of new space company doing this, new technology that, landers on the moon, everybody's got a rocket company, everybody's making parts. It's great, right? Technologies, missions that no one's thought of before, people doing their own deep space communications networks. Very different era than we had developed things in before. So the real question is, how do we organize this to understand what's changing, what's applicable to habitable worlds? So I've defined the space ages, okay? Like other anthropologists before, I've divided into three ages because it's very convenient. The Paleo space age, my father's space age. Right? I grew up, one of the reasons I'm here is I grew up on stories of old captured Nazis and V2s fired into the desert sky. Right? This era from antiquity right up until the Apollo 1 fire, I summarize, is the old space age, and the motto or the ethos of the time was just make it work. Right? People were very insistent on trying it. It was a big thing on experimentation, not a lot of deep analysis. It was a lot of experimentation, very similar to the airplane industry where everybody came from. Dust off a ballistic missile, put something that looks like a satellite on top of it, push the go button, see what happens, fix and replace. Go fast and break things is not new to this industry. At the Apollo 1 fire, we realized that we were not going to complete the national goal of getting to the moon without a little bit more care and consideration. Major redesign effort resulted in the moon landing in 1969. Even though Gene Kranz didn't say it, the screenwriter did. Failure is not an option. That's really the ethos of the time. We are very risk averse. We have to make sure everything works under every condition, particularly on the big so-called Class A important missions. So this middle or mesospace age, I divide into two pieces. The early middle space age, I guess I always wanted to be an anthropologist, and the late middle space age. And the event that separates them is the commercial docking of a servicing vehicle to an unprepared spacecraft in 2020. It's Northrop's mission extension vehicle. You could probably find some other things, but Northrop signed my paper, so that I thought is the best. And previously, things like that would only have been tried by nation states. It is worth noting that that's an entirely commercial endeavor. Entirely commercial. Right, so that's a harbinger of something coming. So I'm now going to say, okay, we're here. I can look ahead and I can see what I'm going to call the neospace age, the new space age. This is John Wilkinson. He was the guy that had a better idea of how to make cannons for the Royal Navy, and those turned into pistons. Those turned into the pistons for Watt's steam engine. And so he's there as a remembrance of the Industrial Revolution because we're standing on the cusp of that revolution. This very hard to read graph here, I apologize for that, is the number of spacefaring countries. And in case you can't see it, there's a very sharp uptick that doesn't include companies, universities, schools with CubeSats, even high schools and grammar schools can participate. This is very different than the era when it was superpowers only. Okay? Because the market that they generate are going to be generating tools that then can be repurposed to keep the cost of development down, and we have to be open to that idea. And more importantly, we're going to have to build that into the architecture. Otherwise, we won't be able to take advantage of it, or we'll have to spend a whole boatload of money to develop our own. And this is why it's very important to consider it now. I'm giving you a little foreshadowing of the rest of the talk. Servicing is really the herald of this revolution. It probably is not going to have a sharp threshold. It's just going to slide and eventually just change. What makes design in the current era, in the immediate recent past, so hard? And some of it's very self-evident, although I should say it. The mission is self-contained. Everything goes in the fairing. I call it the tyranny of the fairing. It's not only a tyrant because of volume and mass limitations. Everybody's got to be ready to go when the train leaves the station. So it becomes a schedule tyrant. So the last piece drives the duration of the program, that drives the cost. Cultural pressure to get everything right the first time and not get it close and maybe bring up a second instrument or make a small change. Communications. In large respect, we still have the same RF communications that we had in the 60s and the early 70s. It's a little narrow pipe, and as I will argue, that will drive instrument costs. We design the instruments to accommodate the communications. The instruments, as you'll see, are one of the more expensive elements. So if we can relax that, perhaps we can knock down the mission. Okay, coming in this new era is more spacefarers, lots of options for either reduced cost launches on little launchers to do experiments, but otherwise a cheap experiment might be much better and more complete than a really expensive 3-year analysis. Large fairings, which opens up a lot of design space, servicing and logistics, the commercial market, new computers, advanced materials, communications, artificial intelligence, the ability to refresh technologies on a more rapid basis. There's probably 5 more things, but you get the idea. So I also want to remind you that these flagship missions are large, complex endeavors. So solving one problem is not going to suddenly make the mission magically cheaper. So there's no silver bullet to knocking the price down by an order of magnitude. You'll hear that, right? There was a Physics Today article written a couple of years ago by some people I know and admire a lot, and they just said, wow, big launchers are just going to change everything, and everything's suddenly going to be cheaper. I sent them an email. They are not talking to me. But what the heck? So again, I want to remind you of the design process, because we're going to go take a quick run at this here. So now we're up to the big question. How can we harvest these opportunities for the benefit of the program? Step 1. What's of benefit? Right? What does the customer want? What's of value? No. How does some aspect of this revolution help? How can we quantify it? How could it hurt? Right? Will that investment in that particular technology or that aspect of the architecture pay off? Or will it have a hidden cost or an opportunity cost? Because just at a meeting, we were talking about servicing, and a bunch of people just leapt into the fact that they were going to start talking about replacing individual boards and components on board. And my head about exploded, right? Thinking of the logistics train and the warehousing and the training and everything. So again, we need to have a discussion about what level is the right level to actually pay off, and we don't opportunity ourselves into bankruptcy. So basically, the things that are valuable are things that reduce cost, schedule, and risk, which is essentially the uncertainty in both of those, and the uncertainty in performance, and the creation of new capabilities or performance levels. Everything after that, I would argue, is not necessarily a benefit to the program. Okay, so we're gonna go through these tables quickly, but what I did was I put all of the challenges here: the closed architecture, technological antiquity, long life, operations costs, funding limits, and then the main aspects here are on the columns. You can look at it in detail, or I can send you the paper that I'm going to write if you want to study it, box by box. So the fact that we can service in logistics, I use yellow for the things that really catch my eye. As you can tell, servicing and ability to assemble things in space is particularly interesting. It allows for post-launch operations, new science instruments, bigger apertures, because potentially with the reduced launch costs, I can avoid a challenging packaging problem, launch the thing in two pieces, put it together, and move on. Packaging the JWST Sunshield was a wicked hard problem. It took a long time, it was expensive. It was ultimately successful. Right? We would not want to wait 20 years for a larger rocket. So it was the right thing to do at the time. Doesn't mean we want to do it again. Replacement, resupply of consumables. Most people think of fuel. That's just because you haven't balanced the spacecraft and managed the momentum properly. But I told you that we want habitable worlds to be ultra stable. That means I don't want a big noisy cryo cooler going thump, thump, thump at 30 hertz, exporting a tenth of a Newton into the observatory. So I can use a doer, which you would normally not consider, because it's going to run out of cryogen. Well, we can just come back with a funnel and fill it back up. A little more complicated than that, but I'm being conceptual here. Ability to install future generations of instruments. Don't have to wait for all the instruments to go. You can define a minimum complement to start doing science and start racking up observatory instrument years and scientific productivity without the full complement. Major programmatic advantage. Advanced communications. Laser comm terminal. You could imagine an instrument that's got its own comm path to the ground. It's not throttled by the decision we made on an observatory 20 years after the instrument. The instruments are a large fraction, and in fact, when you consider multiple generations, you'll see that they're an ever-increasing fraction of the cost. So knocking their price down is one of those high-gain knobs that we want to look at. Advanced intelligence and machine learning. Even today, we are using these tools to develop operations concepts for constellations, to manage them efficiently and at less cost. So we will take those tools developed by others and apply them. Keep in mind, if you're going to operate a long-lived spacecraft, that's an ongoing or recurring cost. So knocking that down is another serious high-gain knob. Again, we talked about the large launchers. There's lots of advantages. A wide variety of rockets can help everywhere from development experiments to flying flight hardware. I'm going to skip the advanced computing. The market. This is one of the most important points. First two great observatories I've worked on, and 4 that I studied for the decadal. The ethos was, if you want something, if you want a technology, you got to develop it yourself. That's an expensive way to go. Market for servicing craft, robotic operations, contracted services, contracted launch, contracted refueling. That's all going to have a commercial basis in the next 10 or 15 years before HWO launches. we don't include it in the planning, we'll wind up paying for that ourselves out of the mission cost, making the design problem even harder. So this is a very important column. Okay, so let's talk about two cases. How am I going to go make a case? Because I have no validated cost models, I have very few projections. So how am I going to establish the value of doing things like making a certain number of the instruments replaceable? Is there value? When do we make those decisions? So let's note that it's a stated fact. Hubble has received a number of instruments over the years. When Hubble was launched, CCDs were in their infancy. There's now CMOS detectors. It's doing science that its creators could not have even imagined. Okay, we're on the cusp of CMOS detectors. They will be old hat shortly. And upcoming, there'll be some super duper quantum gizmo that detects even fainter signals and is even more noise immune and does all kinds of magic things. We want to be able to take care of that and accommodate it as well. Okay, so let's talk about the basic architecture. Usually, there's some kind of mission need for capability, and that's established. And we go out, we search technologies, and the way you get confirmed in the mission is you say, I've got a technology that meets this need. Right? If that technology is on the wrong side of that line, you don't get a mission. So this is a perfectly accurate cartoon. Okay. And you can see here, this moves along in time up to the time where there's a technology freeze, and then that becomes the performance of the system over its lifetime, unless you change it. Okay, so let's imagine that there's some other technology out there. Technology A. Well, technology A is not doing too well. It's much worse than the current technology, and it's not improving very rapidly. Either it's really hard or it's not getting invested, whatever it is. It's just kind of moseying along. It's not very interesting. But let's say there's another technology here. Today is not very attractive. It's not ready to fly. But it has been evolving rapidly. In the case of habitable worlds, this is essentially the conventional coronagraphs. And believe it or not, there's a group developing a photonic coronagraph, a coronagraph on a chip, which has the opportunity of superior performance and vastly decreased cost. But it is not nearly as mature, but it is moving along quickly. Okay. So technologies don't necessarily develop on a straight line. They can develop. So this purple cone represents an uncertainty prediction based on previous history. There's all kinds of cool math about random walks, and that'll all be in the paper. I don't want to drag you through a bunch of formulas, so just go with the story here. Okay? And as we go forward in time, we would take another snapshot and we would get a different projection on the likely development of this second technology. And maybe there's some kind of future mission need. And we would not fly an instrument just to do it better unless there was another need. Right? We've already met the original mission need. And if we had to make the decision and weren't thinking about what might happen, we might say, look, we don't want to fly anything else. So we would predict and use this to predict and say that's not good enough. We're not going to fly it. Or if we keep our eyes on the prize and have the ability to swap instruments, should that technology happen, we would be able to get an improved mission need. So this requires us to keep our eyes not only on the current mission technology, but the entire field to make this decision. If you do that, then you can get a science instrument that continues to produce even when its detector system, its original detector system, has been antiquated out of use. Okay, so here's the other one. Sorry, I'm a bit of a Robert Redford fan, and of course, Somebody told him, in All the President's Men, follow the money. Okay, so he's watching over us. I want to analyze the old and the new way under different mission scenarios and different scientific fields to show how perhaps applying some of these different paradigms would produce radically different costs. So again, I promised you that I would try and quantify this. So I went to the literature. There's some references here. A couple of them I've got my name on. One's from Phil Stoll. So mission cost breakdown, needless to say, is an important topic in the field. And people have studied it and looked, roughly speaking, at how much the different parts of the mission cost. Okay, this is not in dollars. It's in something I call mission cost units. Number one, my employer will let me talk about stuff like that. I'm not high enough in the food chain to use a dollar sign. Probably never will be. That's fine with me, right? And these are really architectural. Again, the point of this is to understand the trends. I'm not trying to predict the cost. I'm trying to see which one is more cost efficient. Okay, so I'm not looking for a little difference. I'm looking for big glaring differences. And for those engineers in the audience, once I write this down in the paper as some god awful looking equation, there'll be a whole section devoted to tolerance analysis and changing the values up and down to see if the answer remains the same. But that's a little too punishing for almost the end of this. So again, you can look at the breakdown of these pieces, whether they break down into recurring, non-recurring, or ongoing expense. Okay, and then we can take those and make an estimate of how much different mission architectures would cost if we did it the old way and did it the new way. So I defined 3 missions. Mission A looks like a typical mission, a 5-year mission with 4-year instruments, a JWST class telescope. And there's not much difference because there's no second act, if you will. Right? So those come out to be about the same. There's no delta, but that's not the way the community is going. I've already told you that by direction from the NASA customer, how the world will be serviceable. So we can imagine, say, a 20-year mission that's got 2 generations of instruments, 8 instruments, similar size telescope. So in the old way, you do that by building 2 completely new observatories and launching. Okay, and you've got to operate them for the 20 years. And when you do all the arithmetic, assuming I've done it correct, it's 2.15 cost units. In the modern new space approach, you build 1 observatory, 1 facility, you launch it, you set up a servicing mission with 4 instruments, you still have to operate it, but you're not buying the second copy of it, everything that goes with it. The spacecraft, the managers, the launch, all of it, right? So that turns out to be 1.5, and SM is the price of the servicing mission. Okay, so this again tells us something important here, that as long as the cost of the servicing mission is at 7/10 of the full mission cost, this could be a deal. Especially if that servicing mission cost were a 20th of a mission cost to you. Then it looks like a great deal. Okay? If we go into an even further future, right? A 40-year mission, 3 generations of instruments. Again, that's 3 complete launches, that's 3 complete mission developments, complete with obsolescence, so you wouldn't be reusing anything and starting from scratch. And operating it, that's almost 4 mission cost units, plus whatever you got to do to make that spacecraft last 40 years. Double it, triple it. Again, that's something I'll cover in the paper. Estimate here is 2.4 years, right? And I even priced in having a replacement spacecraft that you come up and dock, much like the NEV. Think of a space-based USB. Just plugs in, you turn off the old spacecraft, you turn on the new one. You design that in, it's not out of the realm of possibility. Okay, in this case, the Delta is almost a mission and a half. This gives you the opportunity to now fly the other great observatories the astronomers want to fly. And if everybody were to use the same spacecraft, which I've argued in a talk I call Fleet Considerations for the Next Great Observatories, those costs come down even further. Okay, so let's take a break. Let's look at one of JWST's beautiful images, because we're about to get to the summary. We've had a wild ride. Okay, we've kind of defined how we look at the problem of incorporating these new technologies in the architecture, how we evaluate them, how we move from, oh, that's a good idea, to attempting to quantify them. I will guarantee you that the analysis I showed you, don't tell anybody, it'll get better over time. And as we understand things like what is the cost of doing an old-fashioned spacecraft that would last 40 years? Is it 2, 3, 4 times the cost? And understand it. But we've identified things, a critical variable in the suit. How much does that servicing mission cost? We're going to have a viable commercial market that's going to drive those down. We're going to want to watch that and figure out how to incorporate their tools into our design, and not design it ourselves. This is a fundamentally different way of approaching it. So this is as much a cultural problem as it is a technical one. So again, we've talked about how and why to imagine the future, engineer style, not that just sitting on a rock and staring at the sky and just blue sky stuff isn't fun, but that's not how we develop products for our customers. We've discussed the extreme challenge of detecting extrasolar Earths in quantity and the challenge of directly imaging them, the space ages, and why understanding our engineering culture is important, because it drives how we do these designs, and taking a first look at the benefits and the costs and risks of considering their inclusion in the habitable worlds design. And as I hope I've convinced you, there's enough opportunity there that makes it worth doing a lot of these what-if examples in future architecture studies. As I started, this is literally a problem off my desk. So, number one, thank you for letting me practice my closing argument with you today. And with that, I want to return to the opening image and return to the optimism that we started this with. That with careful thought, a little bit of luck and development, we will get to build on time, maybe even early, the Habitable Worlds Observatory, and we will get the best deal for the customer, and hopefully I and my professional descendants get to build it. Thank you very much for your attention.
Thanks very much, John, for an excellent talk. We do have time for questions. Do we have questions in the room? Yes, in the back.
Yeah, on one of your slides it said you're going to hopefully study 25 planets. What does study mean?
So study means identify, establish the orbit, collect spectrum. So essentially establish habitability. So right now, with a whole group, hundreds of them in fact, scientists deciding which are the right spectral lines, what's the right range, what's the right resolution to go collect those spectra. That will be one of the instruments that goes into the observatory. But the idea is collecting 25 establishes enough of a statistical basis to say, is habitability highly likely, highly unlikely? So that's where the 25 comes from.
25 comes from 5 a year for the 5-year guarantee?
Well, you know, that and working backwards from the binomial theorem and saying, you know, can I confirm or deny the probability of habitability is above or below a certain threshold? So 25. It works out to be about 5 per year, but the way it's going to work is the first few years will be establishing whether there's a planet in the habitable zone, then a bunch more visits to establish orbits, and then at the end of the 5 years, there will be the time spent. Because right now, none of those targets are established. So you'll have to look at a greater number of stars.
The real goal is to find another Earth.
The stated goal, yes, that's the ultimate goal, but the stated goal with this mission is to establish habitability. And habitability is broadly defined. So that includes even historic habitability. So there was a time, called Archean, Earth, where the Earth didn't have any oxygen, right? That came from biological processes, but we would go look for the chemistry that was indicative of that early version and say, that's a habitable planet. It might not be habitable for another billion years, but it's going to be habitable. So that's the way they're defining the science case.
Any other questions? Yeah.
Sure. So what was the brightness magnitude of one of the habitable worlds compared to the faintest brightness magnitude of what Webb can do now? Much dimmer?
Let's see.
Times dimmer?
So Webb is in the infrared, the habitable world will be working in the visible, but they're roughly comparable in the 30s.
Yes, in the back, right back.
So I assume you're parking this at L2.
Yes.
So I'm assuming then that you've also made some assumptions and such about launch costs and robotic advances and such to be able to get the servicing mission way out there. Is that correct?
Right now, it's all in that variable SM, but yes, I will be doing that. And of course, that's where I'm counting on the market to come along. There will probably be some key demonstrations. I'm trying to convince our servicing people to go into the lab and put in the same delays that we would expect at L2 to show that a robotic servicing is possible. So yes, there's still some work to do, but I'm assuming that it's possible. L2 is probably not going to be a standard commercial location. It's just not hot property except for the astrophysicists. But that doesn't mean, right, you can't take your car and take it off-road, right? So if somebody has a design for a servicer and a logistics module, we would just repurpose it and send it out to L2. Just have to show that all those loops close. That's part of the technology that would follow if I can show that servicing really pays off to the mission, which I think I'm close to.
We had another question in the back, then you, Stephen. Was there somebody else?
Yeah. So you were talking about the customer. How do they get the money to pay for these giant space observatories?
Your tax dollars are permanent. It's that simple.
So
These large that's not to say that there couldn't be a billionaire or a gazillionaire that says, hey, I want one of these things. Because, I mean, they're expensive to you and me. I wouldn't mind having, 1% of it in my retirement account, right? But in the terms of, uber rich and national budgets, they're in the ones of billions.
Go ahead, Dr. Schiller. Go ahead.
So the money for these and the current studies are coming from NASA tax dollars.
Yeah, I was wondering how close are you to any freeze points in the design? And
I am arguing vociferously that people should not even use that vocabulary. Right? You can't even, nobody's even written down the requirements. You should not be freezing anything. It should be all, now that will change in the next, say, 5 years as the program moves to mission confirmation. That's one of the reasons I'm so animated to make this argument now, because if we don't include it in the architecture for habitable worlds, it'll have to wait till the next great observatory, which would be well beyond my professional activity horizon.
Yes.
You said in your slide that first launch is probably 2040s. What do you think are the top two biggest bottlenecks there to not launching sooner?
Money.
You don't think
Money.
it's tech development or anything? It's just purely funding.
One of my other day jobs is being part of our technology development team. I'm working with and friends with our colleagues at other companies that are working on other aspects. We're actually making very good progress on solving the electrostability problem. So I'm confident that with money and hard work, we could make that schedule maybe even accelerate it.
Two guys over next.
On a cost question, with James Webb came in a lot higher than it was projected. How does that get folded into your estimates for the new systems? Do you account for that, or is it just always a best estimate at the point in time that you make the estimate?
That's a great question. Right now, one of the reasons I've used those mission cost units is right now I'm looking at which option is less money. Right? I'm not even going to try to predict the cost. We have real cost projection professionals to do that. Hopefully we take a different model in announcing costs, and we do it by phases and say, I know how much to get to the next milestone, and take a different approach. Here's a fun exercise for all of you that think aerospace is terribly overburdened. Go home and Google cost overrun. The first 10,000 pages are all civil engineering projects. I've got another talk where we put up a picture of the beautiful Bay Bridge that fell down that was originally supposed to be replaced for $250 million in 3 years, and it took 15 years and $6.5 billion, and humanity has been building bridges for 15,000 years. So yes, we run over, absolutely. And that's a challenge of development, right? And so in the paper I wrote, one of my co-authors is here, we talk about recognizing that and not being too firm and saying it's going to cost this much when you haven't even defined the whole problem.
My follow-up question is, why isn't society educated about that? If indeed
Because
the
it's
cost overruns are very
Because that's,
common, and also that.
I'm going to give you John's own opinion, not that of my employer, the moderator, my long-term friends in the group. I think it's just,
Don't get us fired, John.
it's a hard concept, right? It requires a level of sophistication, most basic. What's it going to cost? Right? When in reality, the cost is important, but probably the most important variable in the flow of money is the funding. Right? What you get every year and when you get it at the right time, especially as you ramp up. All programs plan that ramp up. We just found out today, government has a hard time passing budgets that enable those things to happen. And as we argued in our lessons learned plan, that's a poor way to plan a program. So I think there's a fair amount of sophistication that needs to go into rectifying that. I don't know that I can fix that.
I think we had a couple more questions in the back. Gary?
Yes, Dan Golden's, one of his favorite stories is the birth of Hubble, of the Webb.
Mhm.
When they were looking for a replacement on Hubble. I don't know if everybody here knows about the story, but the essence of it is the astrophysicists came to NASA headquarters and said, let's build a bigger Hubble, as big as we can put into the space shuttle. And he answered, don't answer what I can do, ask what you need. First of all, what's your question? Then what you need to answer that question. So you're leading towards that in your systems
Absolutely.
engineering approach.
And that's why the original Hubble, if I had those pictures up, the original design, 8.5 years. So it was clear that wasn't going to fit into the money box. They went back to 6.5.
Dr.
Do you
Schiller?
have an idea of what ultimate configuration might work?
No.
Somebody has
No,
suggested.
right now, the scientists are arguing over how big a telescope is enough. Fortunately, I have some colleagues that are very sophisticated, and they pointed out that if you make the telescope bigger, you can make the really expensive instruments easier. And so even though it's backwards, if you remember my mission cost breakdown, the telescope is only 15% of the cost, right? And when you go and look at technology development for telescopes, everybody wants to concentrate on the primary mirror. Primary mirror is only 10% of that cost. So that's like a 1% cost. So people have got to, follow money and look where it goes. If you can make a telescope 20 or 30% bigger, and that becomes 13% of the cost, right, instead of 10, but the cost of the instruments drops by 50%, and you're going to build a whole bunch of them, that's where you can save some real money, and that's part of why I'm going to start pounding the drum on this cost architecture. They again essentially get my customer what they want and what they need.
Dr. Schiller.
Yeah, I was wondering, the Europeans have launched a multiple spacecraft system called Proba 3. Have you looked at that one? Because they're using one spacecraft to eclipse the sun, so the second spacecraft can see the corona in an artificial eclipse. Have you?
The one thing that's in between and Hubble is I'm one of the co-inventors of the star shade, which does exactly that. So yes, I'm looking at it, just not for this one. And in fact, people are talking about a star shade for short wavelength exoplanet observations where a chronograph is unbelievably hard. So yes, I've got my eye on it, but I haven't. It's not my day job.
Do we have any other questions? So I have one. Given how the space culture now is changing at a faster rate than technology potentially, how do you think that will impact development of the next great observatory? Is it too soon to say? Am I asking you maybe 5 years too early? Or?
Probably. I think it's one of those that will be interesting in retrospect, right? We're at a generational change. I represent a group in their career that's built 2. Some cases, some of my NASA colleagues have touched 3. The folks that come by that will be the seniors in 20 years have not. And so what we need to do is give them the lessons learned and the tools to make the right decision. So I think it's an opportunity as this turns over. And because they're brand new, they will look forward and not say we've got to design it like it was done in 1985.
Thank you. Any other questions? Yes, go ahead.
Thank you for your talk. You've shown us some first light images. What's your dream of what the first light image from the HWO looks like? What would you like to see?
What is the dream of the first light image from the HWO?
So,
I'm reading the question for the people online.
So the first light image would be, again, probably just a faint little dot next to nothing. So the star extinguished, maybe we'll get to see the whole solar system. Because when we've done the star shade simulations, turn off the star, you can see the whole solar system. So that would be the dream. Although it's possible, because it's supposed to do general astrophysics, that first light image may be something more traditional. But I know all of my scientist colleagues are really looking forward to the images of those first extrasolar planets. Actually, they're really looking forward to the spectrum, but the spectrum isn't very photogenic.
So Ava, we've noted your question online. Would you like to read it and ask John yourself?
Yes, so what do you think will be the hardest engineering challenge in building the HWO compared to the James Webb?
It's the stability. So the need to get rid of every possible source of disturbance. I in fact worked on this problem at the start with our very first technology development. I wrote a paper called Turning Over All the Rocks. And I went into my office and I wrote 48 things that could disturb a telescope that wasn't in the consideration or consideration of Webb because they were too small. And a couple of those are still around. Most of them you can show by analysis are not hard, but because there will be fuel, because there will be moving parts, solar arrays, all kinds of things, squeezing out motions down to a handful of picometers will be the challenge. That will be the hardest part. On the other side, if I were building the instrument, I would say building the coronagraph to the tolerances necessary would be the hardest part for the instrument builders. But I work for the company that's going to hopefully build the observatory.
All right, thank you, John. We have a question online from Alex, who's a 9th grader at South Pasadena High School. He is unable to read the question himself because his mother is sleeping and he does not want to disturb her. So I am offering to read the question for Alex. Yes.
Don't disturb Alex.
Yes. So Alex, here we go. Alex has 2 questions. If it costs a lot to visit and service/fix the telescope, and you're looking at building this over a number of years, would it be worth it to also develop and build a robot tech to ride on board and be capable of doing basic repairs? What a great question.
So that's, quite frankly, Alex, on the list. So I mean, I didn't show you every crazy idea, just the top level ones. And so for robotic servicing, for the replacement of the instruments, for perhaps even configuring the observatory to alleviate the packaging challenge, where that robot arm or arms go is an absolutely great question, and one that I want to study as we look forward to our architecture. And so that's actually a great, very thoughtful question. He got a second one, right?
Yeah. Okay, I don't, oh, here we go, here it is. The other question is, does Northrop Grumman have summer internships for high school students?
Yes, we have.
What a timely question.
Yes, we have a high school internship program for some high schools. If you email me or email Dr. Puchel, we'll see if your high school is included in that program. The answer is yes, but it's usually folks that are closer and can get to Space Park, but I don't want to ever say never, especially not in this forum. So we'll get you an answer to that. I happen to know the people that work on the HIP program, so I'll see what I can do.
Very good. And by the way, Alex, I'm very intrigued by your imagination. So I want to note something. We have a student conference in our region. It's going to be held at the end of March, March 21st and 22nd at Cal Poly, San Luis Obispo. And we have a category for high school students. So I encourage you to consider putting together a paper. The papers will be due in February, so you have some time to work on it. John has already agreed to join us. I'm the Region 6 Deputy Director for Education, so I sort of oversee it. But John is going to give a talk there, and he's going to be one of the judges as well. So I really encourage you to try to join us up in SLO at the end of March. Any more questions? Well, I have another one. I hate to get into too much into the nitty gritty, but the question is if you were to go back and look at how Hubble was actually developed, and of course Hubble was never intended to be serviceable, and the costs for servicing it were probably larger than certainly a future servicing mission. How does that fit into your cost model? Does it still show advantages for serviceability versus launching multiple Hubbles over decades? Because we are talking about getting close to 40 years.
Yes.
Yeah.
So again, the Hubble's also had many of its guts in the spacecraft replace.
Yes.
So the Chandra, same era, no replacement.
Mm-hmm.
Hubble, and interestingly enough, both Hubble and the original AXAF were both designed to be low Earth orbital, serviceable with multiple generations of instruments. When there were budget problems at headquarters, and the phone rang, and we were working AXAF at the time, and they said, remember that budget? If you can build AXAF for 30% of the budget, you can have the money. And a year later, we had an architecture, and we built it in 7 years, still flying. But the first thing we took out was multiple generations of instruments and serviceability, and put it in a completely different orbit to get observing the same amount of observing time from the low Earth orbit. It takes 15 years. We got it in 5 years with the elliptical orbit. So I think Hubble is an excellent example for the productivity that comes with advancing technology in the detectors, as long as the telescope's still good. And it just simply has to be designed to be cost efficient. It was designed in an era when NASA really didn't do full cost accounting, and they got lots of money from the manned space program, and the astronomers didn't pay for the shuttle flights, because if they did, the life cycle cost of Hubble would be considerably different. But the return, the scientific promise, is very much higher, because you weren't stuck with that first generation of CCDs.
Yeah, oh yeah.
And heaven forbid you weren't stuck with the unfortunate accident with the mirror. So I think it's not a watchword for efficient servicing. It is one for superb scientific return from that initial expensive investment in that facility. And so I think, as Alex indicated, we need to make sure that the servicing missions are cost efficient. We talked about that, right? I mean, you don't have an equation, right? Take one quantity, subtract the other. As long as that service mission is less than some easily calculable value, it's cheaper to do it that way. And hopefully we can get it well below that threshold. And so again, by analyzing it, you ask questions of the design to go answer it. So I think as long as we leverage the market, don't design things from scratch, use things that are available, the cost of that servicing will drop, because everybody else is going to want to extend the life of their communication satellites or their broadcast satellite, whatever they've got, because those are substantial capital investments. So we'll ride on the market's coattails.
Absolutely. Thanks for your excellent answer. Well, any more questions? Anyone on?
Sure. In the other stuff category, so I worked on AXAF as well 25 years ago back
Still flying.
at Harvard at the instrument side. You think Lynx will be a go in roughly the same time frame?
God, I hope so. I spent a lot of time on that study. I mean, their real chief problem is mirror manufacture. Because after that, right, I mean, the nice thing
So you
about
made
it,
the mirrors, right? Marshall did the testing, I think.
Perkin-Elmer made the
Perkin-Elmer
mirrors.
made.
Kodak put them together for TRW. I actually did live in Huntsville and ran the B shift on the calibration. I wasn't the boss.
He's got some good stories about that, by the way.
I was a young guy. But yeah, we did the calibration, and then we assembled the observatory here at Space Park.
I worked on the high resolution there.
So you worked for Steve Murray and
Harvey.
Harvey.
Tannenbaum.
Absolutely.
Randy Moore.
So it's still working great. But
SysN, HRC still functioning?
yes, the side of the HRC that broke got resuscitated. So essentially after 26 years, it's fully functioning, and the ops team made magic and recovered most of the operations capability, even in the case of the degraded installation. So it's really a
30
wonder.
years ago. 30 years ago we designed that. Still running.
Yeah, and actually it will be a laboratory for the next version of this talk about how to manage a long-lived spacecraft as it moves along. What did we learn? How do we design for that 40-year required lifetime without charging you Space 2.0 style, right? Which would require all kinds of redundancy and backups, and I didn't want to think about it. It'd be very expensive, if not impossible to prove that it would last that long.
Okay, John, we have two more questions online from Holger. Holger, are you able to answer ask your questions through the microphone, or do you want me to read them for you? Just reply by text if you can.
I'm also here, yeah. I'm here.
Oh, good.
I
Go
was
ahead.
wondering, with the Hubble Space Telescope being the only one in visual light and a bit UV, is there something special about that compared to IR in space? Or is just the demand so low for visual light
Oh, no.
in the field that
The habitable worlds will be, it started out life as this horrible acronym, LUVOIR, large ultra.
I heard about that, yeah.
So it is going to be designed to have significant ultraviolet capability. The real
Good. Yeah, I've heard about Duvoir that I'm aware that that has UV plans. Yeah, it's good to know.
Yeah, I don't. In what I've been talking about in deciding the architecture for service, it's basically my analysis. I would say is wavelength agnostic, right? Because the next version of this, in a year or so, we'll talk about the next great observatories as a fleet and the benefit for building this in and commonality amongst future great observatories, particularly the spacecraft, which then makes servicing and logistics cheaper. You use the same spacecraft, you put them in a common orbit so they can get accessed. Again, driving down the cost of those logistic missions that Alex was worried about, and he'll have to manage, is a way to architect our way to a sustainable future for the field.
Yeah, good to hear that. Yeah, Duvoir, I've heard about that. Yeah, already years ago.
So the other question is, what's the reason the ISS doesn't have a cheap commercial off-the-shelf telescope outside?
It does have astrophysics attached to it. It's a nicer instrument, which is an X-ray instrument. I believe it's got a gamma ray observatory. The reason it doesn't have a visual observatory is, number one, the immediate area around the ISS is dirty. It's kind of filthy, actually.
Yeah.
So, it's leaking, so the partial, it's a significant fraction of a microtor in the immediate area, so it's not a hard vacuum. And of course, the people vibrate the line of sight. So it would be a very noisy observatory, but for wide angle X-rays or gamma rays, that doesn't matter. So in fact, there have been explorers that flew to ISS and had an astrophysics mission, just not an optical telescope.
I will note for completeness, there have been many telescopes, many remote sensing packages that work in the domain that I tend to work in, which is looking at the Earth from space. And it's a very difficult place to work for the reasons John already mentioned. I mean, I joke you need like a windshield wiper or something for some of these systems. So thank you for your questions. Any other questions? Yes, in the back.
I'm just wondering if manufacturing in space, especially spinning a larger mirror, is in the trade space for this. Yeah, seeing as we're so forward with it.
Personally, my druthers would be the next step would be assembly. I don't see the economic case for manufacturing in space, especially given that the mirror itself is 10% of 10% of the cost, and a tiled segmented aperture can be achieved, has been achieved, and so therefore can be done again. I'm also still trying to understand how one polishes a printed mirror in space without the aid of gravity. I'm sure somebody can come up with a clever process, but we don't have an obvious process, so it's just another development. And again, could it conceivably drive down that cost? Yes, it could, but it's going to change the top line by a couple of percent, not the kind of factor 50 or 60% that we're looking for. But eventually, that will happen. I'm sure of it. Just not in the next 10 years, is my guess. Too immature.
Appears we have one more question online. Do you see a telescope being made for the far side of the moon sometime in the future? And let me say, if there is one, and I think there should be one, I think Elon should pay for it, but go ahead and ask for it.
I mean, I can certainly see a radio observatory on the far side of the moon. But then it would take advantage of the fact that it would be very radio quiet. In fact, maybe even it's a group of them with a space element to increase the baseline interferometry. Lots of studies of telescopes on the moon. Believe it or not, the dust is really, it's kind of animated and it's awful, right? So you would think, okay, the dust is just lying there and it's not doing anything. It wakes up when the terminator passes over it, jumps up and gets charged, and so telescopes on the moon tend to get very dirty. In fact, if you look back in the origins of what became the Webb telescope, there was a concept for a telescope on the moon. In the case of Webb, it wouldn't have gotten cold enough, and then we would have found out that eventually it would have gotten dirty. So far side of the moon would be great for probably certain kinds of X-ray, very high energy X-rays. Just put them in a bag and it won't get dusty. Radio. So I can see observatories taking advantage of the very quiet far side of the moon. Probably not a major instrument.
All right, thank you, John.
In that case, we don't really need people up there then, right? Like we could just do this robotically, pretty easy?
I would think that you might need people to set it up, but there are, believe it or not, there's lots of observatories operated by many universities, even some large ones that are effectively remotely operated. The Keck Observatory, you no longer go up to the top of the mountain. There's a control room at the bottom.
I mean, it'd be fairly easy to set up an antenna for radio telescopes.
Yes, right. A lot of people have come up with all kinds of interesting ways of using a crater or using one of the planes to lay out a large, essentially a really large dipole antenna to do just that. So yes, in principle, it could be robotically assembled. You have to think about how it's going to get powered through the lunar night, but in principle, yes, I agree with you. You don't necessarily need people for that.
Thank you.
All right, well, I think we're nearing the end of our time. I want to thank everybody for joining us and thank John especially for his very interesting talk. I was trying to come up with something better than that, but certainly visionary.
I'm going to get you an adjective dictionary.
Yeah, thank you. No, well, where's Chat GPT when I needed him to? So anyway, let's thank John again. So John, on behalf of the Los Angeles section, I want to go beyond mere words and present you with this certificate of appreciation for your talk.
Thank you very much.
Yeah, it's a pleasure.
Thank you very much. Hope you enjoyed it. Thank you for sharing this evening with me and helping me work on my argument to help build the next great observatory. Happy night.
Thank you.
Thank you.
Time for informal conversation up here. I like your point.
Right.
Thank you. Kirby.
Yeah.
Yes, very big, very bright. That's right. I almost made the laser engineer joke. Do not look into laser with the remaining good eye. That's what this is. Yes. Yeah, no, I know.
Oh, thank you. Thank you. And you're so considerate. Yes, it's a pleasure as always. This is certainly a good one. So, yes. Oh.
Just heard me not argue.
Yeah, well, I'm sure, I don't want to speak for him, but I think he would do it. Yes, but I'm happy to do it.
Okay.
I have some thoughts, mostly about the earth, but, you know, talking about the future as well. Yeah, thank you, I appreciate that. When you're finished.
I've been over here.
SpaceX. I have a contact in the August.
We have more pizza cookie on the back and bottled water, so you're welcome to pick up.
That could be a problem. Yeah. I'll have to check the
Thank you. I'll talk to you soon. Thank you.
Thanks, John.
Oh, yeah, yeah.
But oh, you what?
We're gonna try to schedule it for the fall.
Yeah, mine was good. I haven't
Actually, go down there on Thursday for the student.
Sure. Yeah. Well, you don't have very easy to find online.
I was gonna ask you, would you be interested in a program that, March next year?
Yeah. Are you a member of this section in Los Angeles?
Yeah.
Is this for the
science geeks, science fiction world?
Yeah, well, I was a TC chair a long time ago. I
Oh,
spent many
yeah,
roles.
I was TC chair from about 2010.
Yeah, I think, yeah, I was
Slightly different.
around that same time, chair of education.
Start out and say,
Became the deputy director of education.
All right, have a good night. Take care.
So I've
the literary
done a lot of
program
different things
allowed
for
to
the
use
AIA.
is very restricted.
Right.
Yeah, I
Must
all
conform
out at
to
this
the laws
point,
of physics, the
but
laws of
change
economics,
jobs and, getting
the
support
laws of
to
the
these kind of
Right.
places.
Yeah.
and my corporate guidance.
It's not always.
But we
No.
do know.
No, in fact, this year,
that's what they
I've
call
done
hard
a
science.
PIE conference.
Yeah.
San Diego, and I paid
So
my
yeah,
own way.
these,
As a conference chair, I was gonna ask you, where'd you get that?
Yeah, that helped.
Yeah.
Yeah, that helps.
George. $1,000 out of my own pocket.
Yeah.
To work for them, but if they take care of that, I don't mind paying for that.
Some are useful. George Box, he was
Yeah,
a
and as I said, the.
statistician
Science
who
fiction
wrote,
convention,
I've got two of his books.
such.
I didn't know he was the one who said that until like, I said,
B-O-X?
B-O-X.
I'm sure.
Right, but no, he was
on
a
a
few
few,
JPL
as well.
statistical
Yeah.
modeling for things like
You get a lot of young people.
industrial engineering and process.
Oh, it tends to support this whole-
That's, he's the origin of that quote.
Yeah.
Do you do any, do you need Diana models?
Sometimes we can get support from our company, the students are going to be there, and, you know, potential candidates for hires.
Our,
That's true, yeah.
other parts of the country. So I'm sure the.
We just hired
Yeah,
a guy,
yeah.
basically, Jim is a global animal model.
So what sort of people are you
He
looking
just
for?
published a paper showing that virtually every global animal model.
People with jobs.
Yeah,
Ready?
And some guy in his garage in Woodland Hills figured it out.
Well, that's really
JPL,
a good background to have.
IGS, Chinese Academy of Sciences,
Somebody missed something with
JPL, mapping out thick shell 6 parameter,
Trying to figure out
two neuron.
how to make my site.
Like, I should show you the paper. I'll show you
Oh,
this.
yeah, no, I love it, because if I'm in a different environment, I'd love to get out.